So here I'm going to draw a couple of different resonance structures to solve these problems. So you can imagine I just gave in the prompt, draw all potential resonance structures for the following molecules. And your job is just to generate good ones. And the main reason why I've chosen these is because I think will illustrate some common errors and stuff like that. But the thing I wanted to point out first is, generally speaking, there's two different types of mechanisms that you're going to deal with eventually in the course, and that is those where it's the minus that's kind of starting things and driving things, and then there are those that are basically it's all about the plus charges. Where do the plus charges end up? So I like this one because it's kind of a tricky little problem, because it will end up in a strange place relative to what you expect. So the core problem with this structure is that you have a plus on this nitrogen, which is relatively bad, and you have a minus on this nitrogen, which is also relatively bad, and neither one of those is necessarily all that bad, but together that's the reason why you're looking to find a better resonance form. So okay, why is this nitrogen plus? Well, it has 4 bonds, and you'd like to, if you could, give it 3 bonds in a lone pair. You may not be able to, but that's what you'd like to do. Now, what you could do to go ahead and try to solve this problem is to draw this arrow like this. And the reason why you might be tempted to do that is because you've got a minus right there, so you want to take electron density away from it and give it to that nitrogen. Surely that will solve things and make things look better. So let's go ahead and see what happens when I do that. So if I draw that, what's going to happen now is this part of the molecule is unaffected, and then this nitrogen now has a lone pair on it, and then this nitrogen now has a single bond, 2 pairs of electrons on it. This is now formally neutral, this is now formally neutral. Hey, surely that's better, right? Well, except there's a problem. This nitrogen lacks an octet. You have solved the problem in one sense because you've gotten rid of the formal charge, but you did so by creating a new one. This doesn't have an octet on that nitrogen. So even though you could draw that arrow, I am inclined to throw that one out because all things being equal, we really, really, really don't want to have no octet on that nitrogen. So I don't like that potential answer, even though it's plausible in terms of electron movement and it's plausible in terms of getting rid of the formal charges. It does so at too high a cost. You are okay with not having a full octet on a carbon from time to time, but you should be deeply suspicious of any resonance structure where you end up with no octet on the nitrogen. That should make you feel a little queasy. Okay, so if we can't do that, then it seems relatively unlikely that we will be able to solve the resonance problem that way. But okay, let's try it from the other direction. So what happens if I simply take a bond from that carbon and nitrogen double bond? Well, then I'm going to end up forming sort of the corresponding structure on the other side. And here, I like it just fine. Here, I have now a lone pair on this nitrogen. I have 2 bonds to this nitrogen. I've got 2 lone pairs out there. I've got a minus. The plus is now on the carbon. I like that one. I don't have a problem with that one. That one I like a whole lot better. Having said that, there is something I don't like about it, and that is that all things being equal, I'd like to avoid having no octet on that carbon, if I could avoid it. So I ruled out this structure in the middle largely because no octet on the nitrogen is something that I couldn't tolerate, whereas no octet on the carbon I can tolerate. I don't like it maybe as much as some other possibilities, but this one at least is plausible to me in a way that this one really isn't, despite the presence of the formal charges, despite the absence of the formal charges here. Okay, there is one weirder way of solving this problem though, and that's one that will solve the minus part. So right now what I've done is I've spread around the plus, but the minus remains on that nitrogen. And actually, nitrogen, even though it's relatively electronegative, does not tolerate having a minus on it very well. So there's one more resonance form I should evaluate, and that is if I take this pair of electrons from this nitrogen and use it to create a triple bond to that nitrogen, what I'm doing now is pushing all that electron density away from there and spreading around the minus. I'm trying to solve the minus problem. So I push that electron density there, but then I'm creating a 5th bond to that nitrogen, which cannot happen. Therefore, I need to push the electron density out on that side as well. So the result of that is going to be now something that should look very weird to you as well. You're not going to like this one. Nitrogen is happy there. So the end result is that this nitrogen is happy. It has 5 electrons that belong to it, so therefore it is neutral. This nitrogen has 4 bonds so 4 electrons that belong to it, so it's formally positive, even though it has a full octet. And this carbon has a full octet, but is now formally negative because it has 5 electrons that belong to it, even though it prefers to only have 4. So in other words, do I like any of the resonance structures that I've generated? No, I don't. I didn't like the original to begin with. On the other hand, this molecule exists, so this is a real molecule. This is a reasonable resonance structure for it. This one I don't like at all because there's no octet on the nitrogen. This one I don't like much because there's no octet on the carbon. This one, everything has a full octet. The thing that's weird about it is that the carbon has a minus, which should be weird. So I don't like this one because the nitrogen has a minus. I don't like this one because the carbon has a minus. But, and here's the reason why this resonance structure matters, this molecule will react by having nitrogen gas go away. And when that happens, you will end up with a formally neutral structure, which then continues on. Now, that's something that happens later, and for the moment, let's ignore it. For the purposes of generating resonance, just bear in mind that the resonance structures that you could generate would include these. This one I don't like because of the lack of an octet on the nitrogen. The other 3 I like better, and these are potentially the resonance structures that I would most want to see. That's more or less how you would operate with starting with the electrons, so starting with the extra electron density or the bonds and so on. Positive type is going to be more like what I did with this nitrogen, where I'm trying to solve that problem. So this one wasn't a true negative type. This is more sort of a weird combination of both. But this one is a positive type. In other words, I'm trying to solve the problem of this positive charge. And this one's relatively straightforward. Do I have electron density nearby that can solve it? Yes. From right there. Therefore, I slide that over. And what I end up with now is a positive out on that end. And I have a remainder of the molecule just sitting there like so. So that is a relatively straightforward resonance form. This double bond then becomes a double bond over there. As a result of having done that, the electron density that was missing over here now slides over and ends up where the double bond was originally, this carbon out on the end. So that's not particularly good, but it does share electron density evenly across both carbons, which is good. So you might be tempted to try to grab electron density from this oxygen and do something like that. And this you cannot do. It is too far away. These electrons belong to this oxygen. You cannot draw a resonance form that takes those electrons over that way. You could potentially draw a new reaction where this folds in on itself and reacts, but that's not what we're doing here. So this is not available for resonance. And if you're trying to do something, if you're tempted to do something that looks like this, where you take a pair of electrons and you try to push it onto this carbon and so on, I will just simply remind you that you are blocked. Not pictured, but existing right there is a pair of hydrogen atoms, and those keep you from being able to access it. In order for you to perform resonance, what you need to be able to do is have a series of connected pi orbitals available. In other words, this at an empty p orbital, this at an empty p orbital, this at an empty p orbital. All 3 of these then share 2 electrons, and so it's either a double bond over here and empty over there, or a double bond over here and empty over there. Likewise, the way you get these 3 atoms all to have double bonds to each other is each one of them has a p orbital available to do that bonding, and there are 4 electrons available to scatter among them. Whether you decide to push them all to one side and leave a plus on the other, or push them all to this side, you still have fundamentally 3 p orbitals in a row and 4 electrons joining in between. How to do resonance problems? Fundamentally, learn the curved arrow formalism and then make sure you're keeping track of things along the way. Make sure you're keeping track of your formal charges, make sure you're always starting from a bond and going to a lone pair or vice versa, and make sure that you are not violating some problems with implicit hydrogens. Make sure that you are keeping track of where those implicit hydrogens are.